Thanks to the advances in eye-tracking technology with commodity hardware such as webcams, it has become feasible to integrate eye-tracking into applications on user devices. One use for gaze data is the detection of user preferences for objects on a user interface. Such preferences can be used to personalize videos. Videos as they are often don't receive our full attention anymore, but are treated rather like a side activity while the focus of our attention is on our phone or other things. Streaming platforms like Netflix have also recognized this trend and have created interactive movies where the viewer actively chooses how a scene should continue. The problem with these approaches is that the viewers now have to become active themselves and cannot simply lean back and enjoy the movie. By using eye tracking, the viewer's preferences for elements in a scene can instead be inferred from their focus of attention, and scenes can be adapted to their preferences without the viewer even noticing that any adaptation has taken place. In our search of previous work on gaze-contingent movies, we could only find 2 works where the plot of a movie is adapted depending on where the viewer looks. Out of these 2 works, only one has been implemented, but none of the systems has been evaluated with regard to how the personalization of the movie affects the user engagement. To fill this gap, we first designed a framework for building adaptive videos, and we then implemented the system and evaluated its effectiveness for increasing user engagement. Our framework eyeDirect consists of a user interface where the video is displayed and the core component for personalized scene selection. While the viewer is watching a video, the system continuously records his or her eye movements. When the scene is over, the raw gaze data is transformed into gaze features. We extracted 9 fixation-based gaze features, and all of them are area of interest specific, which means they are calculated for a specific area on the screen in which one of our objects of interest is located. The information about the screen coordinates of the object in each frame is stored in the area of interest coordinator. From the allocation of gaze features to the areas of interest, we then infer which element in the scene the viewer prefers. The system offers generic interfaces so that different algorithms can be implemented for preference prediction. Once the preference of the viewer for an element is known, the next scene is chosen. It is up to the movie director to decide based on which rationale the movie continues. One obvious possibility is to display a scene in which the preferred object is the protagonist. But we could also do the reverse in order to direct the viewer's attention to an element that he or she did not much take into account previously. In order to evaluate the effectiveness of the system, we conducted a user study with 175 participants. We used a between-subjects experimental design with 2 treatment groups and 1 control group. Each participant was shown 3 videos, and the first video was a duet performance of the song 2002. We first showed the participants a scene in which both singers were singing together. After 39 seconds, the video reached a branching point, and here the continuation was different for each experimental group. In the control group, we kept playing a scene in which both singers are singing together. In the first treatment group, Anne-Marie started a solo part, and in the second treatment group, Ed Sheeran performed a solo. Note here that we did not use the preference prediction component of the system, but instead we selected the scene continuation randomly. This allowed us to later simulate different prediction strategies and evaluate their effectiveness. After watching the video, we asked the participants to rate 4 measures of user engagement on a 6-point Likert scale. We collected 2 measures for novelty, 1 for focused attention, and 1 for involvement. In the second video, we used a tiled screen to show 2 streams in parallel. Each stream featured a cooking video. The third video was an animal documentary. And at the very end of the experiment, we additionally asked the participants to rate their preference for each element in each video. In the data analysis, we evaluated different preference prediction strategies. Our primary objective was not to evaluate the prediction accuracy of the strategies, but instead we wanted to find out whether, allowing for the remaining prediction error, the tested strategies can improve user engagement. We first tested a naive prediction strategy based on majority voting. We predicted that the element that the user looked at the most was also the preferred one. For each feature, we then compared the prediction with the actually displayed scene. If participants were shown the scene that they were also predicted to prefer, we classified the sample as positive personalization, otherwise as negative personalization. The big advantage of this strategy is that no training data is required, so we can directly predict the viewer's preferences without having to previously collect gaze and preference data for the scene. But we did not find a significant positive effect in user engagement. From previous studies, we know that naive predictions with a single gaze features can deliver very accurate predictions, but only if there is no visual bias in the video material. Often, however, the video elements are different so that one of them draws more attention simply because of its design and not because the viewer is more interested in it. In these cases, machine learning classifiers deliver significantly better predictions. And indeed, when testing machine learning classifiers, we received significantly higher accuracy compared to the naive prediction strategy. We therefore continue to test whether scene selection based on machine learning classifiers can increase user engagement. We found that even though user engagement is visibly higher in the treatment group that was shown the scene that matches their preferences, the effect is not significant. However, when revising the data, we also noticed that there were large differences in the participants' evaluations of the different user engagement measures. We therefore proceeded to evaluate each of the 4 measures individually. The first novelty measure was not significant, and the same applied for the second novelty measure. Thinking about it, this makes perfect sense though. Showing a scene with only the element that the user has already focused on the most will not be perceived as particularly novel. Focused attention, on the other hand, should be higher when the video shows an element that the viewer is more involved with. And concordingly, we found a significant effect. The results were similar for the involvement measure, however, here the effect was only significant compared to negative personalization, but not compared to the generic control group. In a nutshell, we found that the naive prediction strategy does not increase user engagement in our test videos. However, in some cases, it might simply not be possible to collect training data for a scene so that machine learning cannot be applied. In these cases, a valid strategy might be to parameterize salient factors so that the gaze data on elements that draw a lot of attention due to their salient design receive lower weights. Involvement with the video is increased with positive personalization compared to videos where the least preferred element is the protagonist. This finding is especially relevant for videos where a generic scene is not possible. We could think of commercial break videos on YouTube, for example, so instead of showing random advertisements that the user is likely to skip as soon as possible, the advertisement could be chosen based on the viewer's attention while watching the previous video. Focused attention is higher when adapting a video to the viewer's preferences, and this finding can be used, for example, to make educational videos more effective. One example are safety instruction videos on airplanes. The novelty perception is not affected by video personalization. However, we suspect that long-term effects do exist if a person watches the movie multiple times and the plot changes each time. Gaze-based personalization can then be implemented into interactive movies like the ones on Netflix, but instead of having to actively select one continuation, the adaptation would be executed in the background. Overall, our findings show that by using visual attention to personalize videos, we can make the experience more entertaining and better sustain the attention of the audience.